Hello dear students, so this is our 11th lecture on the tensors. So if you remember that in our previous topic we have discussed about that if you talk about to how to construct that this Minkowski matrix and how we can distinguish this. So we can have this matrix also in this Riemannian or pseudo-Riemann geometry, right? So there's a main difference. If you remember, if you have visited my last lecture, so you can you know that this GIG. So it was some that. So this was when you. So this is our that Minkowski matrix, and first one corresponds to our that time component, and the rest three corresponds to our space components, right? So that means, or you can write. So you can represent it by another notation. It can be some plus, minus, 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 right? So इसको हम ऐसे भी लिख सकते हैं, right? Now, so instead of that, you can also change. You can reverse this sign change. So you can put here minus, then here rest of three will be plus. So that means time component minus लेंगे and the space components will be here plus because our ds square that square of the length element it should remain invariant under the transformation from one frame to another frame, right? So this was all about that. So how to construct that this Minkowski matrix, right? So it's a 4 cross 4 matrix. And similarly, if you talk about the Euclidean spaces, we can have this 4 cross 4 this matrix also this matrix. But in this, if you talk about this Riemannian or your pseudo Riemann geometry, so in that case, our that matrix will be so we can have that only that plus plus sign. So that means we can, in that case, our g of ig will be equal to, so that will be that 1 0 0 0. Okay. So this is when you talk about this, if you write this matrix element for this Riemannian or pseudo Riemann geometry in Euclidean space, so you can have plus plus sign. So this is what I wrote here, and this is basically that this Minkowski matrix for this. So we can have one plus sign component and rest will be minus. So that means time component will be plus and the space components will be minus. So that's clear from here, right? Now let's talk about now. So let us calculate first. So in pseudo Riemann geometry, I can write that the square of the length element. You can rewrite this as g mu nu dx mu and dx mu. So mu corresponds to four component. That is. So I'm repeating some of the things. So it becomes so that it becomes clear. So mu it will take those 0, 1, 2, 3 values. So 0 corresponds to our that this time component, and this 1, 2, and 3 corresponds to our space component, means x, y, and z component, right? Okay, let's come back to, so this is clear to us. So ds square is this, right? So we can also prove that, so this g mu nu equal to g, so this is symmetric, right? So we can, so this is clear from here because you can have this g of ij is that's plus plus plus. So that means we can write that g mu nu will be equal to g mu nu. So it is symmetric tensor, right? The symmetric matrix. Sorry. Now if you write now, if I write now our ds square, so that will be equal to, so this will be equal to that dx mu. You can write that g mu nu dx dx, right? Or you can rewrite this as, okay. So this is so if you remember that, so in one of my lectures, so you can rewrite this term as, so this g mu nu dx mu. So this will be equal because this and this will contract mu and mu. So this will be dx, right? So you can rewrite this as, so that means our dx nu is, that is g mu nu dx, because mu and mu will contract, so you will get dx nu, right? So that means, so what does that indicate? So that means if you have some superscript here, so we can calculate that superscript through this matrix, right? So because you are taking this product with that matrix element, right? So taking the product with the matrix element, you will get the superscript of that index, right? So that is how you can get these indices if you talk about this subscript, right? So that means you can rewrite this as, so let me write this as, because our dx g nu dx nu is equal to dx nu, so that means ds square is dx nu dx nu, right? So that means I can rewrite this as, so ds square equal to, so just check that. So because इसके बाद g nu dx mu equal to dx nu, so dx nu, so subscript and superscript, right? So this is clear from here, right? So that means this is simply that you can write this as dx, okay? So that means this is simply that. So that means dx is basically dual to this. So these are duals of each other. Or you can say that this is the reciprocal of that, right? Or in quantum mechanics, you are saying that you have some, if you have two wave functions like psi with psi, so you are saying that this is basically that psi diagram. Psi is complex conjugate of this, right? Okay. So okay, so we can rewrite this as, so that means the ds square is, that means square of the length element is basically the product of the length elements of two length elements. So one length element is dual of another one, right? Or you can say that it is basically the you are taking the complex conjugate of it, right? So that's how ds square equal to this, right? So that means if you talk about now, if you consider any vector, for example, if you take now a dot b, so this we can write as, so this will be a, okay? So this is very clear because, so this is in one of my lecture, if you take the dot product between the vectors or scalar product, so you can represent in terms of that bracket notation. So this is the cat state and this is the velocity state, right? Okay. Or you can rewrite this as, so that will be equal to, so that's equal to g nu. Okay. So this is clear because you can write this as some, in this is you can write a nu and this will be some b nu, right? Or you can rewrite this as, so this will be a nu. Okay. So that means A with B is equal to A nu B. So that means, so you can rewrite this as, so this is simply that the dot product between the vectors, right? So dot product between the two vectors, you can take that the product between, if you take the superscript of this index with the subscript of this, right? That's A nu. So we'll discuss that what's contravariant and covariant. So maybe in our coming lecture, I'm going to discuss that. But this time you just remember that we are basically multiplying that subscript with the superscript. So that simply determines our the scalar product. That's A dot B, right? So this is clear, right? Now, now if you represent now, if we have, so that means if you represent some component like a mu, right? So you need to write the duals of that component. If you want to write the dual of that component, right? Suppose we have some component. Suppose a mu is a component, right? That is, so this is the component of any dual vector, right? Or you can rewrite this as a prime u will be equal to, so that's equal to, okay? So this is clear because for any vector, if you write for any vector, so we can build it in this form. So this is our that transformation matrix, right? So this transformation matrix, you can change it from one system to another system, right? From some primate system to some unprimate system, right? Or you can rewrite this as, so this is, okay, so you can write, if you rewrite now, what's the A dot B here? If you write now A prime and B prime, okay, so that will be equal to, or you can write this as A prime mu, B prime mu. Or you can take reverse of that. You can take first A prime mu, just like this one. So you can write this way also, right? So A superscript and B subscript of mu, right? Or you can take the reverse of that, right? Because the dot product, okay, we can prove that. So we can prove that the dot product, it is that commutative or its domain is invariant, right? So that means we can prove that A prime this mu. So that's equal to, if you take the reverse of that, first take the superscript and then subscript, right? Okay, so this is clear. Now you can rewrite this because this is our that dot product between these two vectors, and we have some. I am saying that this is A mu is some component of any dual this vector. So we can rewrite this term as, so because you can write for any vector, like यहाँ पे हमने दिखाया था, if I have this vector A prime mu, so you can write it in terms of that transformation matrix multiplied by this A with some another indices. So it is related to this transformation matrix, right? So this is clear because if you remember that, so this is our that delta mu nu prime, right? Because if you put that nu equal to mu prime, so you can write A mu prime equal to A mu prime. So you are getting same thing. So this canonical delta, or this is our that transformation matrix, right? Okay. So let's write this A prime mu here. So this will be equal to partial x rho prime mu A rho. Some sigma, okay, you can write some okay, so sorry, so you need to write here, okay, so you can erase this thing, okay, you can write partial x prime mu, okay, so what, sorry, so again I did a mistake here, so this should be B. तो लेट्स हैव अ लुक ऑन दिस. सो यहाँ पे मैंने क्या किया, तो मैंने आपको कहा कि अगर हम यहाँ पे लिखेंगे दिस इज सब सुपरस्क्रिप्ट ऑफ दिस एम्यू प्राइम, so this can be written in this way or you can write in terms of this canonical delta mu, because अगर यहाँ पे मैं mu के प्राइम मान लिखे, if I write this mu equal to mu prime, right, so I will get that a mu prime should be equal to a mu prime. So this is very clear, right? Now what I'm saying now, similarly you can write this a prime mu, but it is now subscript here. So here it is superscript. So this I can write this way, right? And this subscript I can write reverse of that. तो इसलिए मैंने यहाँ पे लिखा partial x rho, partial x mu prime, and this. So because this is delta rho mu prime, this will be delta mu prime sigma, right? Sigma, right? Okay. So this is clear because here this is the subscript, so we can write it in this way through this transformation matrix, or you can rewrite this as, because you can have the multiplication of these two now, right? Or you can write this as, so that will be equal to partial x mu prime, partial x, and what else is there? The arrow bc, right? Okay. So let me check if I'm right. Okay, that's it. Right. So what is this term? If you remember that, because you can have this, this will cancel because this is partial x prime mu, right? And you will get here. clear? Now if rho equal to sigma. So for you can write this as that okay. This is simply that. Okay. So that means this. So what basically यहाँ पे हमने prove क्या किया? We have proved that this dot product it remains invariant, right? So because our a dot a prime b prime equal to a because it's some index row, right? So that means this dot product I can say that it's a scalar. Can say that it remains invariant, right? If you go from one frame to another because it's clear from here, right? Now. Now the next question is, so if we want to convert now, if we want to convert this vector and duals, so if you want to convert a vector into in terms of its duals, right? So that means if we have some vector which is a dual of some another vector, right? So next topic is that is if you write now converting vector. So let us suppose now we have some vector. Let us suppose some vector. Okay. When I'm saying that if we have some vector a mu, so this I can write as a mu that mu a mu. Okay. So this is clear because so again so because mu and mu will contract you will get that a, right? So that means so this can be the dual of this one, right? So that means we can also prove that our G inverse G equal to 1. Right? Okay, because so if this is our G mu nu, so we can also construct it as inverse matrix, right? Because this or that matrix it can be some that 100, so that 4 cross 4 matrix, right? So if you want to calculate this inverse, so we can calculate that, right? So that means if you calculate now G inverse G, that should be equal to identity matrix, right? So you can rewrite now. We can say that. So this is the regular this vector and this our dual, right? So that means for this vector a, so our dual is this thing, right? So this is because this will be again that a mu. So that means if any vector, so we can a mu. The corresponding dual will be a, right? Or it can have this a mu. The corresponding dual vector will be a, right? So this is clear from here, right? So we can prove now. So we have this. We can also prove that G this mu lambda G of that lambda nu. So this will be equal to that delta mu, right? So this is very clear because the mu equal to mu, so this is equal to 1, right? So that means अगर हमारे पास 2 matrices होंगे 4 का 4 matrices, right? This so if this indices will be same that mu equal to mu, so you will get the same, right? So you will get those same matrices, but it will be then G inverse, right? So suppose in cylindrical coordinates, if you have this in cylindrical coordinates, if you talk about this inverse of matrix in cylindrical coordinate system, so if I consider my this matrix is G nu is equal to, तो अगर हमको पता होगा जब मैट्रिक्स जो हम in cylindrical coordinate system लेते हैं, so that is our that 1 0 0 0 rho square 0 0. Now if you write it as inverse of matrix, because this is our G mu, right? So you are talking about the Euclidean space, three-dimensional space, I meant. So we have this in cylindrical coordinates, or G mu is this one, right? So if you want to calculate it as inverse, so that means G. If you write G mu, so this will be equal to So that means जो हमारा G mu था, so that was okay. So just check. So this was our G mu, that's 100. Right? So this was matrix. And if you calculate its inverse, so inverse is simply that adjoint of A divided by mod of A. So that comes out to be this one. So it will be here. It will be 100. It will be 1 by rho square here. When you calculate that A inverse, that's adjoint of A divided by mod of A. So this will be equal to this 1 by rho square A. So if you take the product between them. So when you take the product, so this will be 100, take this is, so you will get 1 here, and then 1 with this, so this will be 0, then 1 with this will be 0, and then second this with this will 0, then this with this, so you will get here 1 by rho square into rho square. तो यहाँ पे आपको क्या मिलेगा when you take their product, so because this is some A inverse like GG inverse, so the product between them will be, so you will get an identity matrix, right? So that means, so you can get here. So for G mu nu and G mu, it comes out to be equal to 1. जो मैंने already आपको लिखा है, right? So that means I can write now. So G lambda mu I can write as. So if you take some this matrix here and A mu, so this will be equal to G lambda mu. So this is basically first one G lambda mu, and now I can write because this is the dual of some vector. So I can write it as regular vector. So this is our dual of the vector. So अगर इसका regular vector हमें अगर हमें calculate करना होगा, so we can calculate it multiplying by that matrix, that G mu, right? So that means I can write here. So this will be equal to, okay. So because mu and mu will contract, so we will get A mu. Because this is our regular vector and this is our dual to this vector. Okay. So this is what I get here, or you can rewrite this as, because this will be that delta that lambda nu A nu. So this is our, okay. So you can write because for that's equal to, okay. So that means this will be equal to, okay. So what does this indicate? So that means यहाँ पे मैंने क्या किया? So if you remember that, because this was the dual to this vector, right? Now I'm basically multiplying now the inverse of the matrix. अगर मैं inverse of the matrix इसको multiply करूँगा to our this dual vector. So that means I am multiplying this inverse of this matrix to this dual vector. It gives me the regular vector. Okay. So that means अगर मुझे, if you want to calculate the dual vector, अगर आपको dual vector calculate करना होगा, so you can calculate it multiplying by the matrix element to the regular vector. Or if you take it as reverse, so if you want to calculate the regular vector, you can multiply. You can calculate that vector by multiplying the inverse of that this matrix G mu nu, right? Multiplying by the this dual vector. So you will get the regular vector. So this is how you can relate them. So that means for every vector G, we can have the corresponding this inverse, that is our G superscript mu, right? So this was all about this, the properties of this matrix G mu nu, and also we can rewrite this if we have some any vector of second rank tensor. So we can have two indices tensors, right? So this was also two indices, but I talked about if we have some vector. So we can write that vector in terms of these matrices also, right? So what I am saying now, so if we consider some vector, if we have some vector P mu, so this is our vector second rank tensor. You can say that is a second rank tensor, right? So you can write in terms of these matrices. So by you can write that P of some alpha beta. Okay, so that means I am writing now. This is the dual. You can say that this is a dual tensor. Okay. So you are writing that dual in terms of our regular tensor of second rank tensor, right? So that will be equal to multiplying by partial x. So here or before that, okay, so we can do that, but I need to write it in terms of that this G matrices. Okay, so we can rewrite this as, so we can write this as G and G, right? So because you need to contract, so you need to contract, you will get mu alpha here, mu alpha and mu beta. Okay, because alpha and alpha will contract, so you will get that T mu and this will contract, so we'll get this because you can rewrite it this dual vector in terms of that regular by multiplying these two matrices, right? Also, if you want to write now the mixed, if you have some mixed tensor, right? Suppose if I write now T of some mu beta, so we can also write it in terms of the G matrices, right? So this I can write as T of alpha beta, right? So because alpha and alpha will contract, so you will get that mu beta, right? So because this is very easy. यहाँ पे आपको याद रखना है कि आपको कौन सा इंडिसेस चाहिए फाइनली, बिकॉज यहाँ पे मुझे क्या चाहिए, so beta is as it is. I need to contract it because I am getting subscript here alpha, so alpha should be in the G matrix, right? So this alpha and alpha will contract, so you will get at the superscript that mu. So this is our mixed rank tensor, or you can have some higher order tensors also, right? So that means so you can write. So this is this matrix. So you can write it in terms of those transformation matrix also, or in terms of delta function, right? So if I have, because I can rewrite this as suppose, yeah, if I have some gradient, we can have some gradient. Also, we can write now. Also, I can write that if I have that partial u prime, so that I can write as uh, partial x some u prime here. This will be new. You can write it this way. So this is some, if you have some gradient, you are taking the variation with respect to these vectors, variation with respect to x, y, or z, right? So that's our gradient, right? Or if you write now some this, if you write some vector of second rank tensor, right? If we have some, uh, if we have some t prime, so how I can write this? So this I can write in terms of these transformation matrix, right? So taking the gradient, so you can rewrite this as, so this I can write as T alpha beta, right? Or let me write it on another page, so you can write that T prime. Okay, so this will be that prime mu, this will be mu prime, okay, and so because no, sorry, I have to, because this will be in the subscript, so you should write it this way. So this will be prime mu. Okay, because so this will be, if you rewrite this as, so we saw that delta sum alpha mu prime, and this will be delta beta of mu prime of alpha. Okay, so this is clear, because अगर यहाँ पे alpha equal to, if I put here alpha equal to mu prime, so this will be mu prime here, and so if beta equal to mu prime, so we'll get here mu prime. So that means you will get same thing, right? So by taking this in terms of this transformation matrix, right? Or instead of that, you can also write for mixed right answer, right? If we have some like partial new also, you can also write this as and t. Okay, so this will be equal to that new prime here. Yeah, it will be new prime, and this will be alpha. Okay, so this is very clear because similarly, I say ये भी मैं ऐसे लिख सकता हूँ that is mu prime. So again, this is our mixed rank answer. How we can convert that this duals into the regular, right? Because this is our regular vector and this is our dual. So मैंने आपको already बताया था, you can write it in terms of these matrices G, or you can also write it in terms of this transformation matrix, right? When you take the gradient, right? So in addition to that, we can also prove that this because we can also prove that this G matrices I can write in terms of these in terms of these transformation matrix also, right? If you go from some unprimed to primed system, right? So that means I can also write those G matrices in terms of this transformation matrix also, right? So let's start. So we know that ds square. So this is very clear, right? Or you can write this as right. So that will be equal to some g of, you can rewrite this as some g of rho sigma prime dx rho dx. Okay, and this will be some right because so this way because our ds square is continuous, so ds prime can be written in this way because it's in some private system the square of the length element, right? Now you can rewrite this term as that's equal to, and let us write this. तो इसको मैं लिख सकता हूँ because this is in some private system. I can convert it in terms of because this is our so this is basically our that dual. This is sorry, this is our regular reactor, right? So you need to convert it into the this dual vector. So dual vectors multiply. उसके लिए मुझे क्या करना है? I need to multiply that inverse of that G matrices, right? G of some. But when you take the inverse, so that is basically when you put the superscript here, right? Then subscript, so that is simply our G matrix, right? तो इसको मुझे dual convert करने के लिए because this is a regular vector length element, right? So we need to convert it into some dual vector by multiplying that inverse of that G matrix, right? So that's very clear, right? So I can rewrite this as you can rewrite this as, or you can convert it because you can also convert it. So that's clear because I can convert it with the help of that G matrix, or you can convert it with the help of those transformation these matrices, right? So we can rewrite this term as, so this will be that partial x by partial x, right? And this will be that dx mu. So मैंने क्या किया? Basically I convert this from some mu prime to mu. Sorry, from the rho prime to mu.